Imagine you're sitting in your Cambridge exam. The clock is literally ticking down. You're staring at a data representation question that looks super straightforward, right? But actually, it's a trap. A carefully designed trap that catches thousands of students every single year. Today, we are going to urgently rescue your grade from a fundamental misunderstanding of how a computer actually processes data. Let's get right into it. So you're asked to add the binary sequence 0111011110 to 11011110. You quickly scribble this down, do the math, and generate the mathematically correct answer of 10100110. If you write that down, you are going to score an absolute 0 in this exam context. It's a catastrophic failure. But why? Mathematically, your addition is totally flawless, but in the reality of an 8-bit computer system, your mathematically perfect answer just completely broke the machine.
And when the exam asks you to explain what just happened, here's the classic student mistake we see time and time again. They write, the answer is 10,100,1100 because I added the binary numbers together. Look, I get the logic, but this completely lacks the precise technical language examiners are actively hunting for on their mark scheme. It totally ignores the physical hardware constraints of the system. To really understand why this fails so hard, we have to rebuild our understanding of data representation from the ground up, starting with the absolute foundation of digital logic.
No matter how unbelievably complex a system seems, everything boils down to the binary number system. It's the basic building block in all computers. But what's really interesting here is the why. Why binary? Well, it's chosen specifically because it consists of ones and zeros only, and those correspond perfectly to the physical on and off electrical states inside the computer circuitry. You see, computers don't actually understand numbers, they only understand voltage.
Okay, let's dive into this. To make those on and off states mean something useful to us, we use an 8-bit system. Just notice how the binary headings double each time as you move right to left. 1, 2, 4, 8, 16, 32, 64, and 128. If we drop a typical binary value below those headings, like 011111001, finding the standard or dinary equivalent is a breeze. You simply add up the column headings wherever there's a 1. So 64 plus 32 plus 16 plus 8 plus 1, boom, that gives us 121. It's just an incredibly elegant way to represent values using nothing but tiny switches.
Now, let's see how this builds when we go in the exact opposite direction. How do you take a positive denary number, something like 142, and convert it to binary safely every single time? Well, the flu-proof algorithm involves successive divisions by 2. You literally just divide 142 by 2, which gives you 71, with a remainder of 0. Then you keep dividing your result by 2, recording those remainders all the way down until you hit a 0 value. But here is the critical step, and honestly where so many students trip up. You absolutely must read those remainders from bottom to top. Doing that gives us 100001110. It's methodical, it's structured, and it guarantees you secure those conversion marks.
In just a moment, I'm going to reveal the precise examiner clue that completely changes your answer to our opening problem. But first, we need the framework that makes that clue super obvious. See, the successive division method works flawlessly for positive numbers. But what happens when the exam throws a negative number at you? Remember, a computer doesn't have a magical minus sign key built into its hardware. It literally only has ones and zeros.
Enter an absolutely crucial concept from your syllabus, 2's complement. This is the designated format used to convert and represent negative denary numbers in binary. Think of it as your official mandatory framework whenever you're dealing with negative values in the 0478 syllabus. It's a brilliant mathematical trick that allows the computer's arithmetic logic unit to process subtraction as if it were simply adding a negative number. And here is the mark scheme approved 3-step process for generating a 2's complement number. Let's say we need to represent negative 67. Step 1. You write out the binary value for positive 67. Step 2. You invert every single binary bit, so every 1 flips to a 0 and every 0 becomes a 1. And finally, step 3, you simply add 1 to that newly inverted number. I know, it sounds a little abstract when we just say it, so let's map it out visually.
And this brilliantly illustrates the whole process in action. Up top, we have our positive 67, 0100011001. The middle row shows the exact inversion of those bits, 10111100. Finally, that bottom row shows the result of adding 1 to the far right side, which leaves us with 10111001.
By methodically tracking your work exactly like this on the exam paper, you protect yourself from those tiny, silly arithmetic errors that can honestly cost you entire letter grades.
Okay, before we jump back to our massive binary failure from earlier, we've got to briefly acknowledge another vital data representation format, the hexadecimal system. Unlike binary's base 2, hex is a base 16 number system. And since we obviously run out of standard digits after 9, hex brings in the letters A through F to represent the values 10 to 15. Why do computer scientists use this? Because it compresses those super long, unwieldy, error-prone strings of binary ones and zeros into much shorter, readable codes. It's essentially just shorthand for binary.
All right, let's shift our focus back to binary arithmetic. When you're asked to add binary strings in an exam, visual structure is literally everything. You must set out your calculation with a dedicated top row for your carry values, 2 middle rows for the actual binary numbers you're adding, and a bottom row for the final sum values. This exact layout, it's what examiners are constantly looking for. If you just scribble down the final answer and get it slightly wrong, you lose everything. But if you show this structure, you capture those crucial method marks even if your final bit happens to be off. Which brings us right back to our opening hook. Remember we added 0, 1, 1, 0, 1, 1, 1, 0 and 1, 1, 0, 1, 1, 1, 0? Well, when we map this out using our strict addition structure, something pretty alarming happens on the far left side. The addition generates a 1 that spills completely over into a 9th bit carry column. And because an 8-bit system physically cannot store a 9th bit, it just drops it. So our final stored 8-bit sum reads 010011100, which is 76 in denary. But wait a second, the denary value of our original two numbers was 110 and 222. That equals 332. An 8-bit system maxes out at 255. So a denary sum of 332 physically breaks the 8-bit limits.
And that brings us to the exact Cambridge-safe vocabulary term you need to know: overflow. An overflow occurs if the result of a calculation is simply too large for the allocated word size of the computer. In our specific scenario, it was the generation of a 9th bit in a system physically built to hold only 8 bits. The computer literally drops the 9th bit because it has nowhere in memory to store it, which spits out wildly incorrect data.
So let's actually contrast our original, kind of weak student answer against the top band upgrade. The low-level answer says, the number is too big, or I added them together. That earns nothing. But the upgraded, top band response states, overflow error. A 9th bit was generated because the sum exceeded the maximum 8-bit value of 255. Do you see the difference there? The top band answer names the exact concept, provides evidence from the calculation, and uses the precise examiner wording. That is exactly how you secure top marks.
Now, I want you to pause for a second and predict something for me. Think about that systematic structure we just used to break down binary addition and 2's complement. How would you apply this exact mark scheme thinking to a totally different challenge, like converting the denary number 2816 into hexadecimal? What are the step-by-step method marks an examiner would demand to see on the page before they award you full credit?
Look, understanding how data is represented, from 2's complement all the way to overflow errors, is absolutely vital. The full rescue kit continues in our next mandatory explainer, where we break down exactly how to structure these answers against the clock, so make sure you subscribe to Ace the Exams to ensure you don't miss it. But until then, I really want you to ask yourself, are you just memorizing binary strings to pass a test? Or are you finally learning how to think exactly like the machine?